Assalamualaikum to everyone. Today we're learning how why money is very why taxes and money is very important. Let's get started.
I told you not to look. Yeah, I literally said.
Money, the season. Let's get started.
That looks really uncomfortable. What are you doing? Well, okay. Just be careful not to fall. You okay there? Dear Tim and Moby, how do snowflakes form? And are they really all different? From Lars. Let's take a look at where they form. Snowflakes are actually made up of snow crystals, or ice crystals that form inside clouds. At extremely cold temperatures, like less than minus 40 degrees Celsius, the water vapor inside clouds can condense directly into ice. At temperatures between 0 degrees Celsius and minus 40 degrees Celsius, water vapor first condenses onto dust particles, making little droplets that freeze. Well, I'm getting to that. Everyone knows that the molecular name for water is H2O. That means that one water molecule is made up of two hydrogen atoms bonded with one oxygen atom. H2O. In liquid form, water molecules bump up against each other and move all around. But when water freezes, the molecules arrange themselves into a more stable formation, the crystal lattice. The ice crystals that make up snowflakes are symmetrical because they reflect that internal order of the water molecules. Yeah. The crystal lattice is the basis for every snow crystal and snowflake out there. A snowflake's shape is determined by the conditions under which it forms. Mostly we're talking about the temperature and the humidity of the air. The colder the air temperature, the sharper the tips of the crystal will be. At warmer temperatures, ice crystals grow slower, making for more subtle shapes. Snow crystals tend to form simpler shapes when humidity is low, and more complex shapes when it's high. Well, those are the snow crystals in their purest structure. They stick together to form our snowflakes, and they continue to grow and change as they fall towards Earth. By the time a snowflake reaches the Earth's surface, plenty of elements have perfected its shape. Hey, not bad. Anyway, it's pretty darn unlikely that any two snowflakes could ever look the same. They all form uniquely and have unique journeys, even though they start out with the same molecular structure. I'm sure Moby can tell us more. What are you seeing, Moby?
Still,
Tim's log, March 20th. Still here on this tiny island at the equator, located at 0 degrees latitude. The time-lapse camera I set up this morning is recording the sun's path across the sky. Cassie and Rita are doing the same thing at 40 degrees north latitude. And Moby's hanging out at 90 degrees latitude at the North Pole. All this to answer a letter. Dear Tim and Moby, what do solstices and equinoxes have to do with the seasons? From Abby. The 4 seasons are caused by the tilt of the Earth as the planet orbits the sun. This tilt makes sunlight hit the northern and southern hemispheres at different angles during Earth's year-long journey around the sun, causing the changes in temperature and amount of daylight that define the seasons. 4 times a year, Earth reaches special points in its orbit where its axis of rotation lines up perfectly with the sun to produce some really cool effects. And today is one of those times. In the northern hemisphere, March 20th or 21st is the vernal equinox, the first day of spring. Right now, the Earth's axis is perpendicular to the sun's rays. Both hemispheres are the same distance from the sun, which means they're both receiving the same amount of sunlight. This will happen again in 6 months, around September 22nd or 23rd, at the northern hemisphere's autumnal equinox, the first day of fall. Good point, Moby. When it's the vernal equinox in the northern hemisphere, it's the autumnal equinox in the southern hemisphere, and vice versa. In other words, the seasons are opposite in the northern and southern hemispheres. During an equinox, the sun looks like it's moving directly over the equator. Here at the equator, the sun rises straight up in the east, reaches the zenith, the highest point directly overhead, and sets straight down to the west. As you go farther north, the sun's arc is lower in the sky. And way up at the pole, the arc is pretty much flat on the horizon. Except for the poles, every place on Earth gets 12 hours of day and 12 hours of night, which explains the word equinox. It comes from the Latin words equus, meaning equal, and nox, meaning night. After the vernal equinox, the northern hemisphere points more and more toward the sun. From where Cassie and Rita are camped out, the sun's arcs get longer and higher, which gives us hotter days and more daylight. About 3 months from now, on June 21st or 22nd, we'll have the longest day of all in terms of sunlight, the summer solstice. That's when the northern hemisphere is pointed almost directly at the sun. It's the first day of summer, and the farthest north the sun rises and sets during the year. After that, the sun will start rising and setting more and more to the south. The days get less and less daylight, and as we pass the autumnal equinox, colder. Finally, on December 21st or 22nd, we'll have the day with the least amount of sunlight, the winter solstice, where the northern hemisphere is pointed as far away from the sun as you can get. This is the first day of winter, and the farthest south the sun will rise and set. Where Cassie and Rita are at, summer daylight can be as long as 16 hours, while winter daylight can be as short as 8 hours. Here at the equator, where the tilt of Earth's axis doesn't affect the sun's path as much, daylight stays pretty close to 12 hours all year round. But the tilt has a huge effect at the poles. The pole facing the sun gets 6 straight months of daylight, while the pole facing away from the sun gets 6 straight months of darkness. Oh, the word solstice comes from the Latin word sol, meaning sun, and sistere, meaning to stand still. Throughout the year, the sun's path through the sky keeps shifting either north or south right up until the solstices, where it seems to stand still for a moment before shifting back in the opposite direction. Yeah, humans have paid attention to this stuff for thousands of years. Ancient civilizations timed their farming and hunting to the changing seasons. That's why solstices and equinoxes became important dates for celebrations and holidays in so many cultures. It's about 1 equinox and 2 solstices too early for that one.
What is your fault? Now you're rushing me, right?
Dear Tim and Moby, why do we have seasons? From Jonathan. Good question. We were wondering why spring can't get here a bit sooner. Hey, did you do that? Huh. Ever wonder why globes are made to lean sideways? The Earth orbits around the sun, spinning on its axis. The axis of the spin is tilted in relation to the orbit by about 23.5 degrees. The Earth's tilt is what causes seasons to come and go as our planet makes its way around the sun. Without that tilt, the seasons wouldn't change, and it would be about the same temperature year-round wherever you lived. When the Earth is here, sunlight strikes the northern hemisphere directly. That makes the days longer and hotter. We call that summer. Meanwhile, sunlight is striking the southern hemisphere at an angle. The days are short and cold. That's winter. When the Earth is on the other side of the sun, the seasons are reversed. Right. Tropical places lie on the equator, the border of the northern and southern hemispheres. The tropics get the full heat of the sun all year round, so their temperatures don't change much. The North and South poles are a different story. There's nothing gradual about the change in season in these places. It's winter, then summer without a fall or a spring. Summer on the Arctic Circle means that it's light outside even while you sleep. In the winter, the Arctic Circle is dark all day long. When do these seasons start? Well, here's the schedule for the Northern Hemisphere. Spring starts with the vernal equinox on March 20th or 21st. Summer begins with the summer solstice on June 21st. The beginning of fall is called the autumnal equinox, and it falls on September 22nd or 23rd. The winter solstice, the first day of winter, happens on December 21st or 22nd. The southern hemisphere begins winter when the northern hemisphere starts summer, and so on. The seasons north and south of the equator are always opposite each other. Ah! You are doing this, aren't you?
Sorry, I have to do it. Bro, I can't even build them lagging that hard. I just needed some fish, that's why I did it. Freaking lagging. Look at my pig, she's running.
Just call me. You just take a couple minutes, a couple seconds.
Yeah, he took me off this bridge.
Man, it's cold. Whoa. Thanks. Dear Tim and Moby, why do some animals hibernate? From Sunny. In the winter, most animals need to eat more to keep warm. The colder it is, the more energy it takes to maintain their body temperature. And that energy comes from food. The problem is, food is often harder to find in the winter. Some animals solve this by migrating. That means temporarily moving to a warmer climate. Other animals adapt to the colder weather, changing in some way that lets them survive. They might store up food beforehand, grow thicker fur, or change their eating habits. And some animals solve the problem by hibernating. No, hibernation isn't just a deep sleep. It's a state of dormancy or lowered body activity that conserves energy. During hibernation, the heart rate goes way down, as low as 5 beats per minute in some animals. Breathing drops off sharply too. Some hibernating animals can go an entire hour without taking a single breath. All this reduced activity results in a way lower body temperature that's within a few degrees of the outside air. In a few animals, like the Arctic ground squirrel, the body temperature actually drops below freezing during hibernation. A colder body temperature leads to a lower metabolism. That's the process of energy creation that happens inside our cells. Cellular activity slows down, allowing the animal to survive on less energy. So, it can make it through the winter with little or no food. Yeah, they do need some energy. Before hibernating, many animals spend days or months eating as much as they can to build up fat. This extra fat insulates their bodies against the cold. And during hibernation, they use their stored fat for energy. Of course, animals have to find a good, protected spot where they can remain undisturbed for long periods of time. Some of them hibernate for months and months, through the entire winter. Others wake up as often as once a week to get rid of waste or to snack. You may have noticed that the animals we're showing are all kind of small. Most animals that hibernate weigh less than 50 pounds. Rodents, marsupials, fish, snakes, and frogs all include hibernating species. Well, the reason is that smaller animals have a harder time staying warm in cold weather because their bodies have more surface area compared to volume. So that's more places for heat to escape. Well, bears are a little bit different. Their metabolism drops a lot, but their body temperature doesn't fall that much. They can also wake up easily. This state of half hibernation is called torpor. Oh, and by the way, hibernators don't all live in northern climates. They may not get as cold, but tropical areas have winter too. Well, some hibernating animals detect when it's getting warmer outside. For others, chemical signals in their brain alert them that it's time to emerge. Kind of like an internal alarm clock saying, time to wake up and find some breakfast. Scientists are still looking into exactly how this works. Anyway, my external clock is telling me it's time to head home. I'd like to load up on dinner, then get under the covers and hibernate till morning. It's a figure of speech.
The next thing we know is heat. Let's get started. First, what is heat? Heat. What is heat? Heat is part of our daily life. And six, we want to explain what is heat. Let's get started.
Dear Tim and Moby, what is heat? From Ashley. Is that your final answer? Yeah, you go phone a friend. When molecules are... Dear Tim and Moby, what is heat? From Ashley. Is that your final answer? Yeah, you go phone a friend. When molecules are exposed to energy, they absorb it and become pretty active. In this excited state, they move around faster and bump into each other a lot. Temperature measures just how fast those molecules are moving. Heat measures the energy contained within an object because of its moving molecules. For example, there's a lot more heat in an iceberg than in a pot of boiling water. Sure, the boiling water has a higher temperature, but the iceberg is a lot bigger. The molecules in the iceberg aren't moving as fast, but there are lots more of them. All that motion adds up to a greater heat energy. The lowest temperature you can get is absolute zero, or about minus 273 degrees Celsius. That's the point where all molecular motion freezes to a halt. Right after the Big Bang, the temperature of the universe was in the billions, and it was too hot for even molecules to form. Heating up an object can cause it to expand because those excited molecules take up more space. Get it hot enough and it'll melt into a liquid. With even more heat, that liquid will become a gas. Heat likes to even itself out. This radiator is on, and it's heating up the room. If we turn the radiator off, the temperature of the air in the room will gradually become uniform. Even though heat itself is energy, it takes other types of energy to create heat. Solar energy, light from the sun, sustains life on Earth. The chemical energy stored inside wood and gas gives off heat when it's burned. And speaking of chemical energy, the chemical reactions that happen inside your body also generate heat. Electricity heats up the metal wires in a toaster. Friction makes heat too, like when you rub your hands together on a cold day. Nuclear energy is stored in the nucleus of an atom, and it creates lots of heat when it's released by fission and fusion reactions. Geothermal energy is the heat that comes from deep inside the earth, powering geysers and volcanoes. Well, Moby, can you tell us what heat is? Hey, get to the point. Ah!
Why are you sleeping? Oh, it's not. No, Tom! Kill his ass! He's so low! Kill him! He's low! I swear, kill him! He's... Bro, I'm getting double people wrong.
This is Moby, a self-published author. He purchased a half-calf caramel macchiato at a local coffee shop. But after writing about the rich history of the rubber band for just a few hours, his drink was ice cold. The cafe wouldn't refund his money, and now he's suing.
I'm really waiting until you say that.
This is Tim, the cafe's barista. He says the customer is always wrong. Plus some know-it-all stuff about physics and molecules. What you are about to witness is real. The participants are not actors. They are actual litigants. Both parties have agreed to have their case settled here before Judge Marilyn Mainframe in our forum, the People's Court.
Your Honor, I'd like to admit this letter into evidence, just as soon as I read it. Dear Tim and Moby, how does a thermos keep my soup from getting cold? Thanks, Mrs. Nichols' class. Now, Your Honor, Mrs. Nichols' class brings up an interesting point. Because, as we've all noticed, hot things don't stay hot. Once soup or cocoa or single origin fair trade coffee comes off the stove, it starts to get colder. And it'll keep cooling off until it's the same temperature as the room. Cold drinks do the opposite. They'll keep warming up until they reach the temperature of their surroundings. Yes, putting a cold drink in a thermos will slow the warming. Or the cooling, if we're talking about a hot drink. So, the plaintiff's foofy espresso drink would stay hot longer, but not forever. Wait long enough, and that macchiato will be room temperature. Thermoses work because they minimize heat transfer. Heat always flows from warmer objects to cooler ones. And the greater the difference in temperature, the faster it'll happen. The only way to keep some coffee from cooling is to put it somewhere just as hot. Is the plaintiff suggesting I heat my establishment to 140 degrees? Because I really must point out, 140 is the only proper temperature for a macchiato. Sorry, Your Honor. I get a little carried away. Now, we've established that heat's always on the move, from warmer to cooler objects, and that a thermos can slow this process down. But to understand why, we need to get closer, a lot closer. Coffee, like any other substance, is made of tiny particles called molecules, and they're constantly jiggling and bumping into each other. In other words, they have kinetic energy, the energy of motion. Of course, we can't see any of this microscopic action, but we can feel it in the form of temperature. That's the average kinetic energy of all the molecules in an object. The warmer something feels, the faster its molecules are moving. I'm getting to the point, Your Honor, I promise. Because all of this microscopic motion is what makes heat transfer happen. First, through conduction, the transfer of kinetic energy by direct contact. When you hold a cup of coffee, your hands get warm. That's because molecules in the hot cup are slamming into molecules in your cooler hands. This is conduction. With each collision, the faster molecule slows down and the slower one speeds up. Multiply that by a bazillion molecules and you can guess what happens. Your hands and the air all around the cup absorb energy from the hot coffee, sucking away its molecular speed, which we read as a drop in temperature. But what if there weren't so many molecules around to bump into? That's one way thermoses minimize heat transfer. They're basically a bottle inside another bottle with empty space in between. It's a vacuum, a space with no molecules in it. So there's nothing there for the molecules in that hot bottle to bump into. Heat loss through conduction happens only at the very top of the bottle, where it's attached to the outer container. Well, there is one type of heat transfer that can go through a vacuum. It's called radiation. It also comes from the movement of particles, but on an even smaller scale. Molecules are made up of atoms, which you've probably seen drawn like this. Those little dots orbiting the center are electrons. When atoms are energized, like when they're heated up, electrons absorb some of that energy, but they don't hang on to it for long. They release the energy as a form of invisible light known as radiation. Molecules that absorb this radiation move faster, same as they would through conduction. That's why the inside of thermoses are often made of shiny substances. Since radiation is a kind of light, these materials reflect a lot of it back inside. Sorry, Judge, just a third and final type of heat transfer to cover. It's called convection, and it happens when a substance is unevenly heated. In convection, heat is transferred by molecules traveling from one place to another instead of just jiggling back and forth. That's why convection only happens in liquids and gases. They're called fluids because they have no fixed shape and flow easily. Heating water on a stove is a good example. The molecules at the bottom speed up, creating more space around themselves. This liquid becomes less dense or tightly packed, making it lighter than the liquid above it. So it rises through the heavier stuff away from the heat source. But then it cools down, becoming denser, so it sinks again. Warmer liquid rises and displaces the colder liquid at the top. This flow of material is called a convection current. This vintage coffee percolator works on the principle of convection, and it makes a wonderfully balanced cup of... Rendering a decision, but I was gonna froth some oat milk for my closing argument. One free half-calf caramel macchiato in a thermos.
Chill. Go to the fight.
The next thing we learn is gas and oil. Let's get started.
Moby, you forgot to fill the gas tank. Dear Tim and Moby, are we running out of gas? Thanks, B. Hey there. That's a complicated question. The short answer is no, not yet. But for a better answer, you've got to know a little bit about petroleum. Petroleum, or crude oil, forms when tiny little sea animals and plants die and then get mixed up with sand and silt on the sea floors. As more and more sediment piles on top of them, they get compressed by immense pressure and heat. Petroleum forms from this compressed organic matter. Because of its low density, petroleum flows upward through the cracks in rock. Sometimes it reaches the surface, and sometimes it gets trapped by dense layers of rock, forming reservoirs of petroleum called oil fields. This oil can be very thin, or so thick that it can hardly be poured. People have known about surface petroleum for thousands of years, using it for sealing cracks in boats, lighting torches, and even waterproofing cloth. But it wasn't until the 19th century that people figured out that they could drill deep down into the earth to pump up reservoirs of oil. They also began to refine crude oil, extracting fuels like gasoline and kerosene from it. Since then, gas and oil have transformed our civilization. Oil is used to make countless products, and its byproducts, like gasoline and other fuels, let people move around the world and even out of this world in ways that would have been unimaginable a century ago. Well, at first, oil looked like a great replacement for coal, the main source of energy for centuries before oil was used. It's more efficient than coal, causes less pollution, and works better in small engines. But burning petroleum still has some major downsides. It releases carbon dioxide into the air, which scientists agree contributes to the greenhouse effect and global warming. And oil spills can be devastating to wildlife. Plus, there's a pretty limited supply. Petroleum is produced naturally, but really, really slowly, as in over millions of years. So we're using it up a lot faster than it can be replaced. Worldwide, experts think there are probably about 1 trillion barrels of oil that can still be extracted. In 2012, the U.S. consumed more than 18 million barrels of oil per day. That's about 20% of all the oil used by the rest of the world. At that kind of rate, the world's supply of petroleum could be used up in just decades. The threat of an oil shortage is actually one of the factors that contributes to gas prices. Even if you don't drive, you've probably heard people talking about the rising cost of gas. You might have even seen that the price of gas at the pump can change overnight, sometimes dramatically. Gas prices will often rise when there's high demand, like during the summer or over holiday weekends when a lot of people will be driving. A natural disaster like a hurricane that affects oil refineries will drive up gas prices too. So will war or conflict in parts of the world that produce a lot of crude oil. To decrease our reliance on petroleum, researchers are working on ways to make engines more efficient. They're also working on techniques that will let them extract even the oil that's very hard to get, but that may not be enough. So they're working on other sources of energy. Yeah, it's a good idea to try to use gasoline wisely. It's hard to get by without it, but there are some simple steps you can take to reduce your consumption, like taking public transportation, combining errands into one trip, or carpooling to school. But I just need a little bit just to mow the rest of the lawn.
Wake up, wake up. Wake up. What's going on? There's a camera. Hey, wake up, wake up. Where the heck are we? I can't even see it, Sam. My contacts in for some reason.
Right here, Chad.
My glasses? Wait, good morning, Chad. Did you write that? Now I can see. It's like a hotel or something. Dang it, Regina. Ew. What is this? Never seen this before. Have you been? Regina, wake up.
Regina.
It's too early, Lee.
What? Are you just pranking me right now?
What did we get here, Chad?
Don't blame me. It's not my fault. I don't know where this is. Come back, Chad. What?
You always send it? Somebody made a lullaby version and played it for us? It wasn't one of you guys? It was you. What is this place?
What's the last thing we remember? What's the last thing I remember? This right here. Not your dream, dude.
We were in the Project Zorgo headquarters. We were in the weather-controlled room. What happened to us?
Wait, are we still in the headquarters right now?
Look out the window. Where are we?
Where are we?
Gosh, this isn't the Black Pyramid.
Let's just get out of here, you guys.
What's up? What? Sure, just unlock her.
Hey, Spy Ninjas, today we're going to do a lie detector test on the Cloaker to see if we can defeat Project Zorgo together and find all the secrets. You ready, Daniel?
And if you lie 3 times, Cloaker.
This is what is required to form an alliance with the Spy Ninjas, and that is what I will do.
Are you sure you want to even do that? These guys should already just trust us. Come on.
Next thing we learn is writing stuff. Let's get started.
You did 3 nice things yesterday and horrible things for the last year.
That's right, Jeff. Angry.
Good morning, class. First things first, there's going to be a test tomorrow on what you learned today.
Being a shady
So, you know,
person?
fair warning.
This is an honorable way to determine trust.
I know that this dude was all about honor. Maybe you guys should have recruited him to the spy ninjas instead of me. You know, maybe
Without further ado,
Ready for the first question.
today's topic.
you need to change.
Dear Professor Tim, I'm a good listener and I pay attention in class. Why do I need to take notes? From Jeffrey. Excellent question, Jeffrey. I'll put it as simply as possible. Listening is not the same as learning. Good morning, class. First things first, there's going to be a test tomorrow on what you learned today. So, you know, fair warning. Without further ado, today's topic. Dear Professor Tim, I'm a good listener and I pay attention in class. Why do I need to take notes? From Jeffrey. Excellent question, Jeffrey. I'll put it as simply as possible. Listening is not the same as learning. You can't truly learn something if you only hear it once. Writing stuff down helps you focus as you listen and gives you something to review later. Now, you may ask, why not just record everything? Because recording gives you an excuse to zone out. If you know you could just listen again later, you may not pay attention the first time around. Just a second. You don't want to write down every word you hear. For one thing, most people can't write fast enough to keep up with a speaker. See how many words you can get down in the time it takes me to say this sentence. The quick brown fox jumps over the lazy dog. If you're focused on transcribing or copying word for word, you can't think about what you're writing. Note-taking should help you break down what you hear. Since you only have time to write down the highlights, you need to paraphrase or summarize the main points. Ask yourself, what details are the most relevant and useful? What are the main ideas, key points, and vital connections? In short, what's the gist of the material? Chances are, your teachers will let you know what's important, so listen to what they say. They might introduce noteworthy information with phrases like, a major cause of the Great Depression was, or 3 consequences of the Civil War were. These clues basically scream, this is important. So be sure to listen for them. And keep your eyes peeled for anything the teacher writes on the board. If I write it down, it's a good bet you should too. That includes dates, names, definitions, theories, and arguments for and against important issues. Yowzers. Can you please read back what you wrote? That's what I was afraid of. Sloppy handwriting is a recipe for confusion when you review your notes. So write clearly. If you're using a notebook, start a new page for every class and put the date at the top. Be sure to leave some blank space in case you need to go back and add new information. And if you make a mistake, don't waste time blacking it out or erasing it. Just draw a single line through it. It's faster, and who knows, you might need that info after all. Using abbreviations and other forms of shorthand will save you time too. Just imagine that you're texting.
Hello?
As long as you can decode your notes later, you should shorten wherever you can. Well, the way you arrange your notes is up to you. Some people use an outline to organize ideas by numbers, letters, and bullet points. Others prefer graphic organizers like word webs and fishbones. Then there's the Cornell system, which divides the page into 3 sections. You take your notes in the main section during class. Afterwards, you fill in this section with key terms, dates, and other study prompts. Finally, write a short summary in your own words here. Now you've solidified the information in your head and created a great study tool along the way. The point is, find a format you're comfortable with and stick to it. Your notes should reflect the way you think. Some people use colors to represent different concepts, and drawings can help you visualize complex structures. All that matters is that your notes help you learn effectively. Well, to each his own, I guess.
5, 10, 15. 15.
What do you call that? It's just like a regular door. The push-pull door, I guess. He became the very thing he swore.
Dear Space Diary, today was fun.
I'm kidding.
Made orbit around planet 47G Alpha Prime. Can this planet support human life? Am about to meet with land.
English, you should also write it properly.
Dear Space Diary, today was fun. Made orbit around planet 47G Alpha Prime. Can this planet support human life? Am about to meet with landing crew to go over their report.
See, proper punctuation.
Right on time.
Way. Servers.
So, tell me, what's your answer to our research question? Should we create a settlement of 47G Alpha Prime?
Wait, guys, we don't mean that.
Great news, but I wouldn't be doing my job if I didn't check out your report.
I used to work for Ted Bundy. We kept
Why, to see what your argument is, of course.
Hopefully no one reads this straight across from left to right like I did.
It's not what I meant.
Give up.
I'm looking for a scientific argument.
Guys, you matter. Don't give up. That's what they meant to say. But yeah, that's not a good place for the signs.
Simply put, a scientific argument is a series of statements leading to a claim or answer to the research question.
Depends on what kind of
Those statements must be based on evidence, observations, or measurements. There are many different terms for these statements with slightly different meanings. But no matter what you call them, they're all reasons to support the argument's claim. Your claim is that humans can survive on this planet. The question is, what is your reasoning?
to say World War II, but I still don't get this. Are you saying
In other words, how does your evidence support your claim?
war? A lot of bad things
Okay, good. The planet has water.
I would move.
That's one piece of evidence. Let's see what else is in your report.
Crunchy vegetable salad.
It's the third planet in the system, just like Earth. And the final piece of evidence, the atmosphere contains oxygen. If your reasoning is good, your argument will be strong. But if not, well,
That sounds good right now.
it won't be. First, we need to make sure your evidence is relevant or significant to the claim.
This is what happens when teachers
Does water make a planet easier to colonize?
social security
Right, people need water to survive, so that's relevant evidence.
individual. Y'all
The
suck.
same can be said for oxygen. It's essential to human life.
By blurring his face, but
Now what about this one? Does it matter if 47G Alpha Prime is the third planet from the sun?
Send me out. They
Sunlight
snitched
is
on this
important.
guy.
It provides energy for living things.
Ma'am,
But the
that's not
planet's
how it
order
works.
doesn't
You take
tell us how
one
far it is from its
basket
sun.
and carry it
And
yourself.
besides, that star might be much bigger or much smaller than our sun.
This looks good,
I think
though.
it's safe to say that being third from the sun isn't relevant on its own.
Wear helmet.
Yep, we're still left with two potentially useful pieces of evidence. But we have to examine the reasoning behind each one with skepticism or doubt.
And this guy's not even wearing a helmet. You're such a hypocrite.
No, I'm not calling you liars. But your evidence needs to be backed up by solid reasoning. Otherwise, it's just information. Your report says the landing team observed rivers, lakes, and clouds. Observations count as evidence, but they can be misleading. You go on to write rivers, lakes, and clouds are all made of water.
Which way do I go? Okay,
Are you
wait,
sure
there's
about
a
that?
sign up there. It says, don't turn left.
This is an example of a false assumption,
But then there's
something
the
we
two
take for granted
signs
without
that say
all the
go
facts.
left. I don't know what to do.
Lakes and clouds are made of water on Earth, but not necessarily on other planets. Saturn's moon Titan has methane lakes, and Venus has clouds of sulfuric acid. We need to take samples to confirm you saw water.
That is literally your job. It is in the name description, that is all you're supposed to
This
do.
is from the lake, isn't it?
This does not make our grammar very good.
We'll just
New
save that for the
vocabulary
lab.
there,
Ugh.
apparently. Not Willie.
Anyway, on to oxygen. The report says we detected oxygen in the air. Humans breathe oxygen. Therefore, the air is breathable. Here, you're making an inference, a judgment based on known facts. It's true. Humans need oxygen to breathe. Your instruments show that there's oxygen in the atmosphere. Does it follow that the planet's air is safe to breathe?
You could totally sue and win. Because you might not open the box when you're talking
Actually,
to
it
someone,
doesn't.
you're like, oh yeah, let me get
Both
you
of your
a slice.
facts are
Oh, crap, I just
true,
cut my
but
hand.
your reasoning
Piece of
doesn't hold
cake.
up.
Don't show us on camera.
Breathable air has
Otherwise,
oxygen,
it's
but that doesn't mean that all atmospheres with oxygen are breathable.
Look here,
See the difference? There might not be enough oxygen for one thing. There might be too much. Or there might be other stuff in the air that's poisonous. Unfortunately, your argument to colonize is looking pretty weak now.
Yo, poor Chuckle, the wrong side there, buddy. This is for the teenager.
Well, you can strengthen your argument with more evidence.
The guy that was putting
Let's
stairs
see what
up
the
his
lab
wall.
says about this sample.
Here you go.
Meanwhile, look at a sample of the planet's air. We'll test out exactly what's in there before we beam down and breathe it.
Follow me on Instagram, links are all down below. And please like and share the
Oh,
video.
no.
And comment below which one was your favorite.
You've gone and filled the ship with air from the planet.
America is a vibrant intersection of traditions and communities. But in 231 years, one thing has never changed. It's time.
When school isn't a place you have to be, why not go to school where remote learning can be as remote as you want?
The next thing we learn is the prime numbers. Let's get started.
But this is like the end of the world I've survived.
Hey, what's going on?
So I think I'm good.
I thought you were.
You didn't say anything. Those are just beeps.
Yeah, call me 2012.
Are you feeling okay?
That, so 2020 is nothing. It's something.
Wait, 2 beeps, 3 beeps, 5 beeps. I see what you're doing. Let me guess, 7 beeps is next? Man, I'm good. Dear Tim and Moby, what are prime numbers? Thanks, Yobani. As you've noticed, Moby's been rattling off different numbers of beeps. Each of those numbers happens to be a prime number, which is a whole number greater than 1 that is divisible by exactly 2 numbers, 1 and itself. Put another way, a prime number can have only 2 factors. So 7 is a prime number because it has only 2 factors, 1 and 7. Okay, I challenge you to find a number other than 1 or 7 that divides evenly into it.
No, like at the movie theater.
Thought so. Okay, based on our definition, 1 can't be a prime number because it's only divisible by 1 number, 1. And a number like 8 is also not prime because it has 4 factors, 1, 8, 2, and 4. Numbers that are divisible by more than 2 numbers are called composite numbers. As for why Moby's beeping prime numbers, I'm not so sure. Communicating with alien civilization. Okay, you've been watching way too many sci-fi movies. The fact is, prime numbers have fascinated human civilization for as long as people have been studying math. We're pretty sure the ancient Egyptians knew about prime numbers, though the ancient Greeks were probably the first to really study them. The famous Greek mathematician Euclid wrote an entire book on the subject. He wrote about some of the most fundamental properties of prime numbers. Well, one of them was called the fundamental theorem of arithmetic. Here's what it says. Every whole number greater than 1 that isn't a prime number is actually the product of prime numbers. In other words, by multiplying different sets of prime numbers together, you can come up with any non-prime number, no matter how big or small. That's one of the reasons mathematicians continue to study primes. They're like the building blocks of all numbers. Breaking any number down into its prime elements is a process called prime factorization. Euclid also proved that there are infinitely many prime numbers. Trust me, they just keep going. Now, you might be asking yourself how we came up with all those numbers. There's actually a pretty simple way to identify all the prime numbers up to a certain point, and it's called the sieve of Eratosthenes. Eratosthenes was another ancient Greek mathematician who lived around the same time as Euclid. His technique for separating prime numbers from composite numbers is sort of like draining water from pasta. First, we make a chart of every number from 1 to, say, 100. Since 1 isn't a prime, cross it out. Then, circle 2, the smallest prime. Next, cross out every even number after 2. Since they're all divisible by 2, they're not prime. Okay, then circle the next prime, 3, and cross out every third number, since they're all divisible by 3. Then circle 5, and cross out every fifth number. Keep going until every number has either been circled or crossed out. Then you've basically drained out all the composite numbers, leaving just the prime numbers behind. Of course, this only works up to a certain point. With bigger numbers, you eventually run out of space to write. Not really. There's no easy formula for generating prime numbers. The biggest prime numbers, numbers with millions of digits, can only be found using computers. These numbers are so big, it often takes hundreds of computers years and years to find them. As of early 2019, the largest known prime number is nearly 25 million digits long. There are an infinite number of primes, of course, so mathematicians are always looking to raise the bar. There are even competitions that award big cash prizes to anybody who discovers the next biggest prime number. No, you can't borrow my laptop for the next 10 years. Crazy robot.
No.
It's a 4 and a 5.
A snake.
40.
I ran a snake and then he
4 and a 5.
40 just got it. And she did.
45. 45. 45. 45. 45.
What I expected my apocalyptic outfit to look like versus what it actually is. Eon said, sporting the Hello Kitty t-shirt. In the movie, yes.
It
Probably got torn off, but it was on the way.
85. 90.
Now we're all just
95.
each other.
The next one in learning is triangles. Now that the 6 triangles are different triangles, let's get started.
Strike?
Why is there a fish?
You're nuts. Okay, time out. Dear Tim and Moby, I need to draw all the types of triangles. Can you help? A triangle is any 3-sided polygon.
I can't imagine what it's like to go to school.
15.
Strike? Okay, time out. Dear Tim and Moby, I need to draw all the types of triangles. Can you help? From Liza. A triangle is any 3-sided polygon. A triangle's 3 angles always add up to 180 degrees. We classify triangles by both their angles and by the lengths of their sides. Equilateral triangles have 3 sides of equal length. Since the sides are equal, the angles of an equilateral triangle all measure 60 degrees. Isosceles triangles have at least 2 sides that are the same length. At least 2 of the angles are equal as well. Scalene triangles have 3 sides of different lengths. Every angle in a scalene triangle is different from every other angle. Correct. Equilateral, isosceles, and scalene triangles are all classified by comparing the lengths of their sides. Yep, I did say that we also classify triangles by comparing their angles. Let's take a look at those. Right triangles have one right angle that measures 90 degrees. The long side of a right triangle is called the hypotenuse, and the two sides that form the right angle. Acute triangles have acute angle is one that measures less than 90 degrees. Obtuse triangles have one obtuse angle. Obtuse angle is any angle that measures more than 90 degrees. So we've got 6 types of triangles. Those that are classified by comparing their sides, equilateral, isosceles, and scalene triangles, and those that are classified by comparing their angles, right, acute, and obtuse triangles. Right, there's some overlap here. Equilateral triangles are also isosceles, since at least 2 of the sides are of equal length. In this case, all 3 sides. They're also acute, since all 3 angles are less than 90 degrees. You might find a right triangle that's also a scalene triangle. An isosceles triangle can be a right triangle, but it can also be acute, or obtuse for that matter, and so on. Well, it just depends on whether you're looking at the sides or the angles. Okay, it's my turn to pitch. Alright, Moby, you ready for the heat?
5, 10, 50, 20, 25, 30, 45,
35.
no, 40.
35.
40.
Paling 30, 35 kata no?
No, it's 40. Hoyo. Okay, say 5, 10, 50, 20, 25, 35, 25, 30, 35, 40, 45,
50.
50.
This is an outrage. I demand a phone
No,
call.
55. Paling gak bakal kata.
No.
A British spy, but I'm an American citizen.
To trick him. You're supposed to know, dumbass. What is after 55? It's like 5 more. Okay?
Dear Agent Moby, what does it mean to be a citizen?
Say 5.
From Dan. You want me to prove my citizenship by answering this letter?
25.
All right, Mr.